Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is on multivariate time series analysis with a focus on data examples. And this lesson, I will continue the example of prediction of river flow, but this time we'll focus on modeling using univariate time series approaches. Again, in this study, we'll forecast the flow of the Chattahoochee River, which is part of the important hydrological system in southeast of the United States. And this is the upper Chattahoochee River watershed is the most important, if not unique, source of water supply for Atlanta area. I'll begin with the modeling of the river flow using univariate time series models. We'll apply the modeling on the log transform time series. I also split the data into training and testing, where the training data include all the years from 1956 until 2006, and the testing data include year 2006 and the first 3 months of year 2017. I'm not showing you here the code for model selection since it has already been discussed for other case studies in previous lessons. The selected order for the river flow time series 1 and 4, AR equal to, the AR water is equal to 1 and MA water is equal to 4, with no differencing identified. That means D is equal to 0, and the difference order for the seasonal component is selected to be equal to 2. With these selected orders, we fit the seasonal ARIMA model as provided on the slide. These are the residual plots for the fitted seasonal ARIMA model. The residuals versus time plot does not show any particular pattern. However, the ACF plot points to large autocorrelations at lags 1 and 12. The histogram and the probability normal plot show that the residuals have an approximate normal distribution. From these plots, the only possible concern is that there is some autocorrelation in the residuals. Let's then apply a test for uncorrelated data using the box test R command. Two important units in this R command are FitDF and lag. The input for FitDF is the number of coefficients in the ARMA model, and this is used because we are applying the box test for the uncorrelated data on the residuals. Since we use an ARMA model with order 1 and 4, the FitDF is equal to 5. The lag input will need to be higher than FitDF. Here we consider it to be 6. We also have the option to use different test statistics provided by the type. The p-value for the testing procedure for uncorrelated data is large, which means that we do not reject the null hypothesis of uncorrelated residuals. Hence, it's plausible that the residuals are uncorrelated. The forecast R function in the library forecast can be used to derive the predictions for the river flow time series based on the seasonal ARIMA model. To plot the forecast, we can apply the forecast function with input the fitted model and the number of lags ahead for prediction, in this case H equal to 15. Then we can apply the plot function to the forecast object. The plot is provided here. The black line shows the observed time series, and at the end we have the predictions along with the prediction intervals. While it's hard to assess how close the forecasts are to the observed time series values for the test data, we can see that the predictions have high uncertainty since the prediction intervals are wide. Next, we'll extend the ARIMA model to account for exogenous factors such as temperature and rainfall. Just like the VAR-X model, this is called ARIMA-X. The ARIMA-R command allows specification of exogenous factors through the XREG option. As provided here, both the temperature and rainfall time series are considered exogenous factors in modeling and predicting river flow. We apply again the model selection. This time, the selected order for ARMA are 1 and 4, whereas for seasonality is 0, indicating no differencing for the seasonal component when accounting for the exogenous factors. Next, I fitted a model and plotted the residuals. The residuals are here. The residual plot versus time does not present any pattern. The ACF plot of the residuals resembles that of white noise, indicating plausibly uncorrelated residuals. The residuals also have an approximate symmetric distribution, an approximate normal distribution as provided by the histogram and the probability normal plot. Here we apply once more the test for uncorrelated data. Similarly to the ARIMA model without exogenous factors, we do not reject the null hypothesis for uncorrelated residuals when applying this testing procedure because the p-values are large. We can obtain the forecast similar for this model, for our ARIMA X model, similar as before. The R code used for extracting the point forecast and the lower and upper predictions intervals are in the R code files for accompanying this lecture. On this slide, I'm comparing the predictions using the ARIMA without exogenous factors in the upper figure and with exogenous factors in the lower figure. I specify the same scale for both plots for comparison. The prediction using ARIMA without exogenous factors are not better than when accounting for exogenous factors. The point predictions for ARIMA X do not have as high uncertainty as when using the simpler ARIMA model. In summary, in this lesson, I provided the univariate modeling for the river flow data example. Thank you.